Hello everyone, welcome back to Math for Machine Learning series. In the last video, we explained transformations, rotation, scaling and shear and saw how matrices can stretch, rotate or distort space. Today, we're going one step deeper. But before we talk about how matrices change vectors, we need to understand how vectors relate to each other. Do they bring new information or are they just duplicates pointing in the same direction? That's exactly what we'll cover today with three big topics: linear independence and dependence, basis vectors and spanning of a space, and finally, matrix rank. By the end of this video, you'll see how all these three connect beautifully. So we'll start with part one: linear independence and dependence. Let's start with the big question. How do you know if a set of vectors adds new information or if some are just repeating others? So, a set of vectors is linearly independent if no other vector can be made by combining the others. Formally, if we have v1, v2, vn, they're independent if the only way to satisfy c1 v1 plus c2 v2 plus and then cn vn equals to 0 is when all coefficients c1 c2 up to cn are 0. In plain English, you can say that you cannot mix or scale the other vectors to recreate one from them. We'll take an example here. Take two vectors in 2D. v1 equals 1 comma 0 and v2 equals 0 comma 1. You can say that vector 1 points along the x-axis and vector 2 points along the y-axis. You can't make one from the other, no matter how you scale them. They're independent and together they form a basis for a 3D space. Now we'll move on to linear dependence. So vectors are linearly dependent if at least one vector can be made by combining the others. Example, we'll take v1 equals 1 comma 0 and v2 equals 2 comma 0. So if we look at this here, vector 2 is just 2 times vector 1. It doesn't add any new direction, so they're dependent. If we need to talk about the geometric meaning of them, in 2D, two independent vectors span the full plane. Dependent vectors lie on the same plane. While in 3D, three independent vectors span the entire space, while dependent vectors lie in a plane or a line. To summarize, independence provides full coverage of space while dependence collapses into a smaller surface space. But why does it matter in machine learning? So features in a data set that are dependent are actually redundant. Example, if we consider height in centimeter and height in inches as two features, they carry the same information. In linear regression, dependent columns prevent us from finding unique parameter solutions. So, machine learning model loves independence. It ensures each feature contributes unique information. Now, we'll move on to part 2, basis vectors. Now that we know independence, let's talk about basis, the backbone of vector spaces. So what is a basis? A basis is a set of vectors that are linearly independent and they span the entire space. You can think of a basis as a coordinate skeleton of a space. Once you know the basis, you can describe every other vector as a combination of these basis vectors. For example, in 2D space, the standard basis vectors in 2D are e1 equals 1 comma 0 and e2 equals 0 comma 1. Any vectors x comma y can be written as x times e1 plus y times e2. Here, e1 and e2 are independent and they span the full plane. They form a basis for 2D space. Similarly, the standard basis in 3D is e1 equals 1 comma 0 comma 0, e2 equals 0 comma 1 comma 0, and e3 equals 0 comma 0 comma 1. These form the x, y, and z axis. Any 3D vector can be expressed as a combination of these. We can also change the basis. Span a space can have different bases. For example, in 2D, b1 equals 1 comma 1 and b2 equals 1 comma minus 1. These are also independent and span the plane. Changing the basis changes how we describe vectors, but not the space itself. In ML, this is used in PCA to find a new basis that represents data more efficiently. Now we move on to spanning a space. The span of a set of vectors is the collection of all possible combinations of them. Example, vector A equals 1 comma 0 and vector B equals 0 comma 1. That particular span covers the full 2D plane. If you only have one vector A equals 1 comma 2, span is just a line in that particular direction. So to summarize, span tells us how much space our vectors can cover. A basis is the smallest set that fully spans it without redundancy. Now the next topic is the matrix rank. Finally, we'll tie everything together with this particular topic here. So the rank of a matrix is the number of linearly independent columns. Think of each column as a vector here. The rank tells you how many unique directions these columns span. For example, we'll consider full rank. So you can see the matrix A here. The columns of matrix A are independent, so rank equals to 2 here. This is a full rank. It spans the entire 2D plane. We'll also consider this second example, the matrix B here. So if you look at this matrix B, the second column of matrix B is just 2 times the first. Only one independent column, so rank equals 1. Geometrically, this collapses the 2D plane onto a single line. So if again we have to repeat the geometric meaning, rank 0 means all collapse to origin, rank 1 means flattened to a line, rank 2 means it spans a 2D plane, and rank 3 means it spans full 3D space. Rank tells how a matrix transforms space. But why do ranks matter in machine learning? Ranks give us the number of independent features in data. The lower rank of the matrix, the less redundant the data is. In linear regression, if rank is less than the number of features, it hints towards multicollinearity, which means no unique solution can be found here. While in PCA, we look for lower rank approximations that preserves as much info as possible. To summarize, matrix rank measures the dimensionality of the information in your data or transformation. So everything we've learned today connects back to the transformation. When we apply a matrix, the rank tells us whether we preserve space, compress it, or collapse it. So that is all for this video. If you found this helpful, like the video, subscribe, and keep following along as we decode the math behind machine learning one step at a time. And I will see you in the next video again.